All right, today we are starting chapter 12. We have an introduction to multivariable calculus here in section 12.1, and we're going to define a function of two variables. All right, so let's think back to when we were in algebra and we first learned about functions. All right, so we would learn that f of x was just another name for y, and this function would take some value of x that you would plug into the function, and it would plot it to a point in R2 with the x coordinate, and then the y coordinate was defined by the function f of x. All right, so a function in algebra was basically taking R1 and was mapping it to a point in R2. So these functions of two variables are going to move that a step further and map R2 into R3. So these functions are going to take as their input some point x comma y, and they're going to map it to a point x comma y, and the z coordinate is going to be defined by this function f of xy. Okay, so just like f of x was another name for y, now f of xy is another name for z. So just kind of an easy example, let's write down something that might be a function of two variables. It can be any combination of x's and y stuff that you know from algebra. So we could have like a 3y squared, we could throw a square root in here, some trig, some log function, anything you want, some constants. All right, and so then you might want to find f of an ordered pair. So let's pick something easy to plug in, f of 4 comma 1. So we're going to do exactly what it looks like. Everywhere there's this y, I'm going to replace it with that 1. And everywhere there's an x, I'll replace it with a 4. And we get an output. So a little bit of arithmetic. 3 times 1, 5 times 2, plus 2 on the end. And that gives me -5. All right, so this tells us that this function, if we were to graph it, would have the point 4 comma 1 for the x and y, and then -5 is the z coordinate. All right, so let's explore this a little bit more in GeoGebra. All right, so here we are in R3, and I've got a function of two variables defined up there in the upper left-hand corner. That one's a little hairy looking, negative square root of some x and y stuff, and then +7. And I'm going to turn on a point in the xy plane, you know, on the floor. And I'm going to turn on these sliders to kind of let the point roam around the xy plane. So anywhere down there in the xy plane, any point that I feel like I'm going to ask GeoGebra to plug it into this function f of xy. So then it's going to associate this point xy with a point directly above it. To make that easier to see, I'm going to turn on a vector. There's not actually anything vector-y going on with multivariable functions, and just connecting it with the point in the plane. So it's mapping that point x comma y to a point in R3. All right, so if I let GeoGebra do this blue point thing all day long, it's eventually going to trace out a graph of the function of two variables. And it's just a surface in R3. All right, and another thing this vector is doing for us is kind of the 3D version of the vertical line test. So remember the vertical line test in algebra? We said a graph was only a function if every vertical line passed through the graph once. Okay, so we mean in R3, we're saying each vertical line that passes through a point in the xy plane is only going to have one z coordinate associated with it. All right, so we've accidentally stumbled across a couple of functions of two variables so far this semester without realizing it. So we're going to see if we can identify these with what we already know. So I've given us a function of two variables, and all we have to do to recognize this function is to remember that f of xy is another name for z. So I'm going to replace f of xy with z. And if that doesn't look familiar yet, let's move all the xy stuff from the right-hand side over onto the left. So I'm going to add 2x to both sides. So I'll have a positive 2x over here. Subtract 4y from both sides. And then the z's over here on the left already. And all that leaves me with is an 8. All right, so that should look like the equation of a plane to you. And it is. So this is a plane with normal vector. Remember, the normal vector to the plane was the coefficient of the x, y, and z. So 2, -4, comma 1. All right, so, and you can imagine a plane would pass that vertical line test. If I had my vertical line vector floating around the xy plane, it would only hit the plane up in space at one point each time. All right, the next one that we can recognize is this one, f of xy equals x squared plus y squared. Again, remembering that f of xy is another name for z. Okay, this one actually ends up being one of our quadric surfaces. It's been a while since we thought about these, so let's pull out that handout. All right, here we are in our quadric surfaces handout, and the place you want to be is at the elliptic paraboloid on the second page of that handout. And remember, our equation, our function was z equals x squared plus y squared. And that's an elliptic paraboloid where the a and the b there are both equal to 1. So we kind of actually have a circular paraboloid. All right, so you can also kind of picture that this one would pass that vertical line test. If I kind of roam around the XY plane with my vertical line, it's going to hit this elliptic paraboloid in only one spot. The only other quadric surface that's going to qualify as a function of two variables would be right below there, the hyperbolic paraboloid. Okay, that sort of horse saddle. That is also going to have only one z coordinate associated with each x and y coordinate. The other ones, like this elliptic cone here, you can imagine any point that's in the xy plane is going to hit 2 points, once on the top cone and once on the bottom cone. And that comes from the fact that if you were to try to solve for this, for like z equals a function of x and y, eventually you're going to have to take the square root of both sides of the equation to get rid of that square on the z, which is going to leave you with a plus or minus, where z is going to be plus or minus. The plus is the top half and the minus is on the bottom half. And all the other quadric surfaces have z squared, so they're not going to qualify as functions. All right, so we identified this one as an elliptic paraboloid. All right, and in the next video, we're going to talk about the level curves of a surface, which can sometimes help us to identify what a surface looks like if it's not one that we already know.